Yeah, this is good. So, yeah, I'm probably drinking right after the talk. No big. So, hi everyone. I'm starting to talk. But V8 by example. We're going to talk about the JavaScript compiler that everybody loves. Hello. Hey. Yeah, works now? So the JavaScript compiler you all know and love, it's used inside Node.js and everywhere. And let's start talking about the compilation pipeline and how things work. And hopefully by the end of the talk, by knowing about the internals of the engine, you'd be able to make a case for what code's faster than not so fast code. And you'd be able to write really good code and, you know, pester your coworkers with like comments like, hey, change this, because it's slow. But yeah, a little bit about myself. I'm Ujjwal. You can find me on Twitter and GitHub on @risercooking. You can post a rant or DM me. I'm a core collaborator in Node.js. I am also one of the maintainers of Electron, and I contribute to this ecosystem that we all love on different projects. I'm a student, so I'm still at the university. I was working with Google Summer of Code a while back, and I'm a speaker. If it's not obvious enough, I put in the slides just to reinforce it. But what is V8? Let's get in the meat of the talk. Like, how does V8 even work? What even is V8? And let's try to get done in like 15 minutes, and I'll just leave. But what is V8? So V8 is developed by Google. It is a JavaScript runtime engine. If you're fancy, you'd be more about ECMAScript. And it also runs WebAssembly now. It's used inside Chromium and all Chromium-based browsers. So that's Yandex, Opera, Samsung for you. And it's also powers Node.js. So for if you ever like that weird thing the backend devs keep talking about, yeah, it's running there as well. But how does it work? Like, how does it really, really work? Let's get into it. It's like no bullshit. So you write JavaScript code, right? You get the source code, and it's parsed by the engine, but it's not. Like, so how, like, by show of hands, how many people have used any third-party code with their JavaScript apps before? Everyone? No third-party code. But like, yeah, if there's something you know about, you know, JavaScript bundles, is that they're huge, and if you're using something like jQuery, you're probably not using any of the code that was shipped with your app, just using like $.add maybe. And it doesn't make a lot of sense to just parse the whole like megabit byte package that you shipped. So instead of directly parsing the code, V8 actually checks if it's immediately executed, if it's inside an IFI. And if it is, it's parsed eagerly, is the term we use for it. But if it's not, it's lazily parsed, which means it's like eager but slow. and it's not completely parsed. And V8 just checks if you actually ever end up using any of that code. And if you do, it's eventually eagerly parsed. But otherwise, it's just out there. This technique saves a lot of time. This technique actually leads up to the formation of the AST and scopes, which are like a data structure, the abstract syntax tree. It's a data structure that holds your code. So it's like at this point, V8 doesn't care about if you use tabs or spaces. You should not use tabs, but that's a discussion for the other day. But yeah, it's a programmatic representation of your code. It's like a data structure that holds your logic. And this AST and these scopes are then fed to the ignition interpreter, which produces Byte Code, which is run on the virtual machine. It's kind of like the JVM if you do any Java, which is probably not a good idea either. But like, yeah, and the code starts running on the ignition, register machine, but interpreters are slow, right? I mean, everybody knows that interpreters are not as fast as like compiled languages, and we're moving towards compiled languages. So I had an idea. I had this like path-breaking idea, which was like, let's not be slow. Nobody has this idea before. So, but it's like, let's use a jet compiler. So we can compile JavaScript ahead of time because we have no idea what your website's gonna have. Maybe you're just like playing Tetris with your friends. So let's use a just-in-time compiler. Just-in-time compile your code. And yeah, we use a lot of techniques. Don't bother reading any of these. And we made a just-in-time compiler. It's called Turbofan. And it's optimizing your slow code by using profiling data that is collected through the Byte Code. Yes, V8 contains profiling data about your code. If Google was not collecting enough data, they're also collecting data about how you use JavaScript. And it produces optimized code, which if you fail the standard that Google set for you, it'll be de-optimized. And you get back to square one with the Byte Code. So this is kind of how the pipeline looks, and we're good. Everybody get it? Let's go home. How you feel about this? And this is pretty much how I felt about this. Like, what so let's take a couple steps back. We're talking about how does V8 work. Let's talk about how a compiler works. So the basic idea behind a compiler is that you have like some source code that you want to run on your machine. So you transform that into targeted machine code for your architecture. It passes through a parser, as we talked, which produces an abstract syntax tree, then through a compiler, which produces an assembly program. So we're going to do a lot of assembly today. And then goes through an assembler, which produces relocatable machine code, and then a linker, which produces target machine code. So is that simple enough yet? Probably not. So let's try to make it a bit simple. So like, see all this weird stuff that nobody actually cares about? It's called the compiler. So yeah, it's just the compiler inside the compiler. How cool. But there's bad news for you. V8 isn't that simple. Why would you ask? Like, why could we not have a simple compiler? Because ECMAScript is slow by default. So let's analyze this situation. As I said, I have this path-breaking idea of not being slow. But how? So we have this, I got this idea, everybody got this idea, it's like, let's use this technique called speculative optimization. Like, cool. But what even is speculative optimization? Because nobody has a clue. So yeah, speculative optimization is guessing what is about to happen based on what has happened in the past. So V8 is retrofitted with a crystal ball that kind of helps it, predict the future. And that's how it like completely optimizes your code. But no, it's basically, so based on the inputs that you give to your functions, it kind of tries to guess what the future inputs would be. And why does it help? Like, why does a technique like speculative optimization would help? So in order to analyze it, let's say, what are the top 3 reasons why a certain JavaScript function might need optimization? So why do you think JavaScript functions are slow? First thing, the most important one, I guess, is dynamic types. So because JavaScript is dynamically typed, you kind of never know what kind of types are going to come, and you can never optimize it. And if you could optimize a program for dynamic types, that'd be amazing. Secondly, of course, there's dynamic types, and yeah. So there's a lot of reasons, the top 3 according to me. But yeah, so this compiler thing needs to go. It has to be a bit more complicated. And we break it into 2 sections. It's called the baseline interpreter and the optimizing compiler. So this is kind of how it works. We saw this before, but the AST is actually fed to the baseline interpreter that produces baseline code. It's like not quite there when it comes to speed, but it just works. And so that's why it's baseline. Like, and the byte code run, but it collects profiling data, which then is fed to the optimizing compiler along with the function, which is optimized. And the optimized code runs until it is de-optimized. When is code de-optimized, we're going to see, but yeah. And the compiler is nobody but V8. So V8 is the compiler, Ignition, as we talked about, is the baseline interpreter, and Turbofan is the optimizing compiler. So yeah, this is pretty much this. That's great, but how does it even work? So let's consider an example, right? So this is a simple example. This is some high quality production code that I had to steal away from my company. But let's see how the abstract syntax tree actually looks. So I'll just get out of this session, and this is my code. I just run the and try to print the AST. So yeah, this is how the AST looks. It's pretty intuitive, so I just like leave you people to it if it's in the slides. But yeah, it's not too intuitive because it makes no sense, but I've got you. So yeah, I mean, this is kind of how it looks. It's boring, but it's telling vital information. So there's a function at some address. Nobody cares about the address, sad. But yeah, it's of certain kinds and certain count, which also you don't care about. But it has the name add. So that's something that's valuable and you store it. And it has parameters, which are just two variables with x and y. It has just one statement, which is return. And it returns the addition of these two variables, x and y. And these variables are then, the scope is then resolved. If these did not exist like in the same scope, then it would like go above and check for it. And once this is done, we could use this data structure to generate the byte code. So I'll try to, instead of printing the AST, try to print the byte code. So here's the byte code. Let's hope you like assembly. So let's step through it. Yeah, everybody likes assembly, right? It's the most intuitive language. This is kind of the byte code for the add function. So it has 3 parameters. Wait a minute, we only passed 2. What is this sorcery? But the fun fact is, like, it has a implicit first parameter, which is the this pointer, or like as nerds call it, the receiver. But it has 3 arguments, which is this and x and y, kind of how you in Python you always have self as the first argument. And then it has the frame size of 0 because we did not define any variables. It has 4 lines. So let's check. First line is just checking the stack for like any problems and setting it up. The second line just loads the second argument into the accumulator register, and the third line actually adds the first argument to what's already stored in the accumulator, which is like the second one. But what is this 0? What does this signify? So 2 important things are happening here. That's why the 0 exists. Firstly, of course, there's addition, and addition is as simple in JavaScript. If you had noticed, like you could add strings and stuff. So it's complicated. And the 0 that we saw, it's profiling. So as we talk, we're collecting profiling data, and it's stored in special vectors called feedback vectors. And that's we'll talk about it in just a bit. But yeah, you're returning the data stored in the accumulator, and it's done. But wait, what about speculative optimization? We never did any of that, right? But yeah, now that we have the baseline code running, we can actually put that profiling data that we stored in the feedback vector to good use. Oh, remember this? Remember when I told you JavaScript addition was complicated? See for yourself. So yeah, let's try to understand this. No, I'm kidding. Let me break it down for you. So yeah, if you have 2 numbers, it's fun. Great, adding 2 numbers, complexity 1. If you have 2 strings, it's slightly more complicated. You got to concatenate them. It's complexity n if you're just using buffers. And if you got 2 objects, then things are going to get weird. And we need to talk, like, really, why you're adding 2 objects. But yeah, we kind of got this. But how do we make that assumption? How do we kind of, assume that a number is going to get passed into the function? Remember the feedback vectors where we're storing the profiling data? Let's see how they are. So you'd have to, in your code, add a statement called debug print to see the stuff. So I'll just quickly And now if I just call it, you'd see a chunk of text, which is pretty much useless, I mean. But this is the part that we care about. It's the feedback vector. And what's so special about this? If you see over here, it says a lot of stuff. It's invoked 1, so it says invocation count 1 and all these things. But like the important part is that remember this slot 0 that we saw? It actually stores something. And it stores the type that was passed in the function. So it says signed small. But then you're like, wait, there were no types in JavaScript. But internally in the compilers they are. So the type that we passed is called signed small, which is like really small signed integers. And if you probably don't believe me, so let's try doing something like this. And if you do it, the type will change. It will go from signed small number, which is like now we have floating points, so they're not signed integers anymore. But yeah, this is useful information. How though, we don't know yet. But what's important is there a method to all this? Like, how do you know about these hidden types, and like, how do you optimize for them? So yes, there's a cool way of tracking this information. We call the feedback lattice, and I'm going to run you through it. So this is a simple diagram of how it looks. You could pass absolutely nothing into your function, which is kind of sad, but then it could have the type none, or you could pass everything to it, and then nothing would make sense. But if you pass just small signed integers into it, they'll be signed small. Number, if also floating points are involved, and number or oddball, if stuff like undefined, true, false, null are passed, then those are oddballs. And strings, so they have like a completely different class, completely different tree for them, and big integers. They're not a part of any existing optimization pipeline, so they're just hanging out there. This data in the feedback vectors is used to finally optimize your code once a function is hot. So when is a function hot? Like in JavaScript lingo, we call a function hot when it kind of becomes the bottleneck of your code. When it's running again and again and again, and it's choking your code to being one of the single points of failure, where it's like, yeah, this single function is kind of why my code is slow. So let's actually see what happens by explicitly triggering optimization. So we had this simple code. Let's kind of make it hot. And it's done. So I'll just also do it on my so we optimize it and call it again. And what would happen is, so it's being called. And if you print out the optimized code, it looks like this, which is like good old assembly. What we just do, we use the flag to actually trigger the optimization. But yeah, this is how it looks. So I guess everybody understands this. We could just
give it.
So let me kind of like make sense of this for you. This is the prologue, so this is the part you can just skip because it's just for nerds basically, and we're all cool, right? But it's just setting up the function for actually doing anything productive. It's just setting up the registers and the accumulator. Then you check if the first variable, which is x, is a small integer. Then check if y is a small integer. So you're just checking if the assumptions that you earlier made are actually true or not. Then you actually convert them into word32s, which is like a format that the CPU could optimize for. Same with y. Then you add them with an overflow check, just in case you're doing something insane and everything blows. And then you convert the result back to a small integer, and then you just return it. So let's try something fun, right? Because it's getting too boring. Let's de-optimize the function. But I'm obviously kidding. De-optimization is not a laughing matter, but if I do this and trace the de-optimization, kind of get a really, so you kind of get a really convenient, message, which makes you like really understand, this is why my code's de-optimized. That's so helpful. I mean, I could just print this out for users and they could tell me. But usually it's like not very convenient, so let me try to make sense of this for you. So first off, you see at the top that it's de-optimized because the parameter that you pass is not a SMI. It assumed it to be a SMI, it's not. And the exact value that was not a SMI is a heap number 1.1, which is the new value that we passed. Down below, you'd also see 2.2 just coming up, so like even if the first one did satisfy it, the second one would definitely fail. And that's the pro tip. If you don't want your code to be slow, try to stick to certain types. Makes things easier. I just like to thank certain people for this. Benedict, who works at Google, and all these people actually work for Google. They helped build the engine and helped me with the talk and everything. Jacob, Sigurd, and everybody else for the V8 team. But I actually also want to thank the organizers for making the awesome conference. And thank you all. Paldies.
So, who understood everything? And isn't like completely blanked out? Everybody understood everything. Or nobody understood nothing? I come confused. I have one question, so you have time to prepare. Are those like percentage calls, I can call them as well, or is it like a special thing for you?
So if you check, I was using a flag which was allowed native syntax. So you can't just use them inside the browser, because like where would it print it out? But you could use the debug version, and then you could just
the debug version of V8?
V8 or Chrome or whatever.
Or
even Node.js, like you could do this in Node.js.
Oh, sweet.
Yeah.
Okay. I hope everybody knew it already, and I was the only one who didn't know this. So, more questions.
Yeah. Hi. Since most of us are writing their JavaScript using TypeScript, you have the types already, right? So when it transpiles to JavaScript, can you already like do all this optimization, or?
They actually like most of the stuff that TypeScript does is like mostly tied just to the compiler. So once it's compiled, it's just JavaScript and without any types. But the best part is that if you impose similar types inside your application, then you kind of like the good practices that I talked about, you're kind of imposing yourself those onto yourself, and that could mean that like you hit the optimizations more often than other people, and you don't de-optimize that much. So it's not exactly a bad idea to use TypeScript, but it's like it doesn't matter that much. Like you could do all of these things without TypeScript.
Well, where was the?
Yeah, thank you. And I just don't understand how like this optimization, de-optimization thing help anything with compilation of JavaScript.
In what sense do they?
I mean, you say like first we try to optimize our JavaScript code and then we de-optimize it.
Okay.
So how like anything?
So yes, as I said, like one of the biggest problems that actually makes code slow in JavaScript is the fact that like stuff as simple as addition, it's so complicated, and it's complicated because we just cannot assume anything. We kind of like if you pass in an object, it can be a number, it can be a string, but it could be like pretty much anything else, right? So this is why like the JavaScript spec itself is slow. There's so many checks and so many conversions to do, and the way it optimizes your code is by kind of trying to assume that you just, if it just assumes that you're passing numbers, then it doesn't have to do any checks and it doesn't have to do any conversions. But so it's kind of trying to find patterns inside your function usage and your JavaScript usage, and kind of assuming that everybody is a rational person and they'll just kind of do the same things over and over. which is like actually a pretty terrible thing to do because people would just throw in weird values all of a sudden, and that's why the de-optimization step even exists, because V8 would make these observations that yeah, everybody is cool and they're just passing strings to this function, and then all of a sudden you throw in a big int, and then it's like, oh, maybe you deserve this.
So are there situations where you can basically on the compile time initially when you load JavaScript already assume that this function will always be optimized? I don't know, for example, you define like add 1, 2 and it's the only place that it's called actually. Can you assume something like that and just forget about it, or is it
I mean, you'd have to like give V8 enough data to actually go ahead and optimize it. If you notice, I like added an extra call which is like optimize function on next call, like manually optimize it just after one call. But it's like V8 would first like notice if there's any like if any function is in fact really hot, and if it's hot then it will try to make sense of it. But if like you just all the functions like function like thrice, then the benefit of actually spending the time to optimize it might not be as much as just running it de-optimized, I guess.
Yes.
Does it mean TypeScript generics make the functions de-optimized by default?
That would be true, yes, because like it's the same function. Actually, so if TypeScript generics are compiling to different JavaScript functions, then if they did that,
yeah,
then that would not be, but
if
they
it's
don't.
a different number of parameters and so on, then
yes, so TypeScript generics only help TypeScript, they don't help JavaScript. So essentially it's like this, they're compiling to the same JavaScript function, but it's like just for the compile time checks. So it's actually if you're using generics instead of normal types, then like you yourself making the way for de-optimization, you'd rather actually, instead of writing a generic, make two functions.
Yeah, yeah. Thank you.
More questions? So maybe I'm stupid and you can just say it outright. So WebAssembly, you don't ship JavaScript, you ship something else, right?
Who ships?
Like me, I create an application and the output is WebAssembly.
Okay.
So it means that it's going to be faster. It's faster because it's Byte Code. How that whole thing works?
If you're using WebAssembly, you don't have to go through this pipeline. There's another compiler for in V8 which we call liftoff, and WebAssembly just goes through that. But because it's already assembly, it doesn't need to be run through the same problems. And because it's like the problem is JavaScript. JavaScript is slow, and that's the problem people are trying to solve. So WebAssembly doesn't have this kind of same problems and doesn't need to be dealt this way.
Cool. I just want to say V8 team has like the coolest names for their features. Like
yeah, thank you.
I think. Oh no, there's a question.
I guess it'll be a short one. Can we, like as a JavaScript developer, can do anything when we like going in React just to help compile and our code to be faster?
Yes, so that's actually, thanks for the question. The V8 team is, as I said, they're trying to find patterns inside of JavaScript code, common patterns, common conventions, and they're trying to optimize your code for those. So if there's a pattern that you think people follow, or if there's a pattern you think should be optimized, then you should kind of reach out to people. For example, there's this certain pattern that nobody had bothered to like notice ever, is that starts with and ends with usually like always have a single character. So it's like if it starts with single character, or if it's ending with single character, and people don't usually have like huge strings for that. And that certain use case, it's so common, but it was never optimized. And actually, I'm pretty smart about it, but like I shipped the optimization for that recently. It's probably in Chrome now. But yeah, I mean, if you think there's a pattern that people are using, if you think there's a pattern that should be faster than it already is, then make an issue or send anybody a DM, anything.
Which question we didn't ask you? We are having this long Q&A session because you talk so fast.
Okay.
But which question did we miss? Like
Which
question? Yeah, like question about React. That was a good question. Which is the other one? Is there any question we haven't asked you?
So there's one really good question somebody came up with, was like, why can't you store multiple multiple optimized versions of the code? Why just store one and de-optimize and optimize again and then de-optimize? And one of the reasons that we don't know how many versions you'll have to store, and people are already pretty obnoxious about Chrome like taking away a lot of their RAMs. Like, is Google mining Bitcoin on my computer? Probably not. But yeah, one of the things about JIT compilation is that it takes a lot of RAM to work and optimize your code. It's actually, V8 just in Chrome 74 shipped a JIT-less mode, which makes it consume RAM less. But yes, we can't ahead of time know if you're gonna need two versions of the same function. So just deal with it. Maybe write two different functions for two different kind of types.
All right, that's it.
Thanks.